So we've learnt that there's an enormous amount of something we can't see in the universe. We call it dark matter because we can't see it. We know it doesn't emit light because we don't see it, and we also know it doesn't absorb light. If it was opaque, it would block the light from more distant things, so it's got to be transparent. What actually is this huge amount of stuff?
Well, we do know at least a little bit about what's in the universe, because when we go back and take the universe when it was a giant nuclear reactor about a minute after the Big Bang, we can very accurately measure how many atoms there were in the universe, or how many baryons, as we like to say. And when we make that measurement, we very clearly get a number, which is that there was about 1/7 of the amount of stuff, of gravity, that we see in the modern day universe in the form of atoms back when the universe was a minute old.
So some of the dark matter is made of normal atoms, protons and neutrons, but the vast majority has to be something that doesn't engage in nuclear reactions, something different.
Exactly.
So-called non-baryonic dark matter. And one possibility for this was it's in the form of lumps, so-called massive compact halo objects, or machos, or maybe black holes in vast numbers orbiting around the outskirts of the galaxy. So if dark matter really wasn't the form of lumps of massive compact halo objects, so-called machos, how could we detect them? How could we find out if this is true or not?
Well, in the late 1980s, an astronomer named Bohdan Paczynski had an idea. He knew about the idea of gravitational lensing. And he thought, imagine something like a black hole that you couldn't normally see pass directly in front of a background star. Then it would, by gravity, magnify the background star and make it appear brighter. And then as the star or the black hole moved along, it would be fainter again. The only problem, for a very reasonable amount of machos in the universe, you'd need to look at 1 million stars just to see one in a year.
But a group of astronomers, both here at Mount Stromlo and in the US, thought about this and said, so if any one background star, you need to find stars in some nearby galaxy to use as background sources, once in 1 million years, something dark would go in front of it and make it appear brighter. You'd also make multiple images, but they're going to be too small to see. But if it's 1 in 1 million years, sounds like a pretty difficult project. But if you look at 1 million stars, you get one a year. If you look at 12 million stars, you get one a month.
So in 1993, in this telescope, astronomers started an experiment that did exactly this. The Macho experiment looked at 16 million stars continuously.
As you can tell, this telescope is no longer in working order. It was burnt down in the Great Canberra bushfires of 2003, along with the rest of the observatory. Before it was burnt down, the telescope was fully automatic. It would actually open itself at sunset if the weather was clear, check the weather, focus itself, pick its targets, analyze the data, and even ring the astronomers up if it discovered something interesting.
Yeah, I remember it fondly because it used to send me messages on my telephone. And on the 18th of January 2003 in the afternoon, there were fires about, and it sent me a message that said, temperature out of range, 73 degrees Celsius. And I knew the telescope was in trouble.
Here's the remains of the superstructure of the telescope. This was winched out of the burnt-out dome and dumped over here after the fires. The main mirror used to sit down here. It would take the light and focus it. That was originally bolted on the bottom here. That would bounce the light up towards the middle there.
So the light came up from the primary mirror, entered the top end of the telescope here, and was split into two colors, red and blue, by a device we call a dichroic. And so part of the light went off here to the side, and the other went out to where Paul is standing out the back. Now this telescope was unique because it was equipped with a 64 million pixel CCD array, the world's largest digital camera. And so it was able to collect data faster than any other telescope before its time.
So, what did this telescope discover? Did it actually discover the dark matter of the universe was in the form of machos?
Well, in 1993, just a few months after it started observing, it did find the first microlensing event where a star was magnified by an unseen object. So it really could be that the universe is full of these machos.
So great excitement for a while, but as more experiments were done, more data was accumulated, the statistics became a bit clearer, and it became very obvious that what they were detecting was not actually lensing due to dark machos, but actually lensing due to normal stars, usually dwarf stars in the front of the galaxy, lensing those in the back. So actually the project ended up being able to rule out the possibility that most of the dark matter is in the form of machos. Most of it must be in some other form.
But the experiment is still useful because it is a way for us to still today detect things we cannot otherwise see. And so in the course on exoplanets, we will actually discuss how we can find planets like Earth around distant stars using this technique. So we know the missing matter in the universe doesn't appear to be atoms or baryons, the stuff we see here on Earth. And we also have reason to believe it's not in the form of machos, of condensed pieces of matter. So another idea is it might be a new type of particle, for example, a weakly interacting massive particle, so-called WIMP. These particles would be a new type of matter that we haven't yet discovered.
If this is the case, and you do the numbers, it indicates there must be very large numbers of them, and they must be going right through our bodies and the Earth as we speak. These particles must interact with normal matter so weakly, be so wimpy, that they can pass right through us and through the Earth, and most of the time have absolutely no effect on us.
So neutrinos are a weakly interacting particle, but the problem is they're not very massive. We go through and we count out how many neutrinos there should be in the universe. We fall many orders of magnitude short, so we need something else.
Yep, so we know neutrinos exist, but they can't do it. So we want something that's a bit like a neutrino, but heavier and a bit harder to see, to absolutely fill the universe and be flooding through us as we speak.
So it's a great idea, but we need to come up with a way to look for these things. And I can think of 3 possible ways to do it. One way would be to just create them in the lab.
Yes, so we could go to something like the Large Hadron Collider, and you'd smash particles together, and presumably if you smash them just right, some fraction of the collisions would produce one of these, whatever they are, these WIMPs. You wouldn't see it because it would manage to escape quite happily out of the detectors in the Large Hadron Collider, but maybe if you did the energy balance, added up the energy of everything else that came out of the collision, you'd see that something was missing, and you could work out how much was missing, what direction it went, and that might be a clue for a WIMP.
So another way to look for them would be taking advantage of the fact that these things don't interact much, but occasionally they do interact, and there's so many of them that we could imagine building a detector which would go through and be able to detect the collisions that occasionally occur between these and things on Earth.
And there are a number of these experiments around. They are generally placed down mines so as to keep rid of all other forms of background radiation, because you're absolutely swamped by the other forms of radiation going through. And there have been a few claims of detections, but at the moment they're detecting you 2 ± 3 pings, which is of course consistent with none at all. So we're not quite there yet, though some people are quite excited about it.
And the third way I can think of doing this is if this stuff really does interact, it probably would interact with itself. And if it interacts with itself, then you can imagine creating 2 times its E equals mc² mass energy and form some energetic particle from when this thing interacts with itself. It would produce a new particle sort of out of 2 of these colliding together, and we might be able to detect those things.
And the place where these interactions would happen most would be around the centre of our galaxy, because that's where the density of these things is greatest. And there is indeed a hint from an experiment on the International Space Station that it does seem to be some flux of energetic positrons from around the halo of our own galaxy, the central region of our own galaxy. And at least some people think this might be a sign of dark matter particles annihilating each other, though there are actually several other possible models to explain it as well.
But at this point, we really don't have any solid evidence, so we're going to have to keep looking.
And the really scary thing would be all the forms of evidence we've talked about so far have relied on dark matter interacting with itself or with normal matter at least a little bit, like neutrinos do. But it's entirely possible you could have a particle that doesn't interact with normal matter at all except through gravity. So it can pull us with its gravity, hence explain the rotation of galaxies and gravitational lenses and everything else, but it can go through any amount of matter without interacting with it. In this case, you could never create it in the lab. No matter how good your detector is down in some mine shaft, you're not going to see it. It's not going to annihilate. If that's the case, we might never know what dark matter is.
Yeah, I can't think of any possible way of detecting it then. So we would really be stuffed in that case, wouldn't we?
Indeed. So it could be that it does interact with matter in some case, and it could be that we'll hear a press release from CERN or from some underground basement lab tomorrow saying, yes, we've discovered dark matter, and we'll have to re-record this lesson. Or it could be that, if we were filming this 100,000 years from now in our hyper-evolved future selves, we still won't know the answer.
Time will tell.